Come on in, everyone. Feel free to ask any questions. Class is getting ready to start, of course, but we're going to be firing up in a second, so I got a little bit of time. Anybody have any questions? You know you have your second midterm tonight that's quote unquote face to face. Hopefully you just got my email. I'm sorry I didn't warn you earlier. Hopefully I saved somebody's trips, but I know it wasn't very much time. I'm sorry for that. I sent it off yesterday afternoon, but I noticed it never came through, so I didn't notice it until just now. Well, about 30 minutes ago. 40 minutes ago, because I sent it out at just before 4:40. So everybody hopefully knows now that you do not have to go to lab. You don't have to go to campus to do your test, but you do have to have a computer that can run Respondus lockdown browser, Respondus monitor, and has a webcam, which generally speaking, all my internet students have that capacity. If you didn't, I asked you to go ahead and text me immediately and we'll work something out. Obviously that's I didn't get any of those texts, so I suppose that means everything was all right, but it could have been that y'all didn't get my email. So I'm allowing it now, but you can talk to me right at the end of class if you want, and we'll work something out. If you don't have that capacity, I might just have to make up a new test for you, and you have to take it tomorrow or something like that. But anyways, anybody have any questions about any?
Yeah, I have a question.
Yes.
Yeah, so I just read your email because Tony showed me it. But if we do go in person, do we still have to turn our webcam on too? Or like, is it still the same
There
thing?
is
Because I don't
there's no option for in person. Just I mean, unless we have to set up something at a testing center or something like that. Just because
Oh,
lab instructor have the night off.
oh, is Professor R is not there?
Yeah, she's not going to be there.
Okay. So we're
Uh,
all just taking it at home.
yeah, and it even gives you a little extra time if you need maybe 30-45 minutes to study. As long as you
Okay.
start it within an hour after class, I'm going to be okay with you starting it then.
Okay. Okay. Thank you.
You're welcome, Angelica. Anybody else? Does anybody foresee any problems with you being able to do that either from home or somewhere you find comfortable and quiet and conducive to testing? Like I said, it doesn't have to be home, but you just need access to good, reliable Wi-Fi, and you need the ability to run a webcam so you can do respond to this lockdown browser and respond to this monitor, and it's got to be able to run Canvas. So
Professor,
yes, you tell.
one of I'm not sure if it's just me, but I saw the second midterm was due yesterday by midnight.
Yeah, that was initially set up. It should be fixed now. If it's not, I've got to check it right at the end of class. So it'll
Okay.
be ready to go for everybody. But yeah, it's not supposed to come available until literally right after this class.
So is it going to be due by the end of tonight midnight, or is it going to be due like 10 a.m., 10 p.m.?
It's no. So what I'm doing is I'm giving you a full hour, and you should have it done by midnight. Or excuse me, a full 2 hours, and you should have it done by midnight. So in principle, you can start it as late as 10 p.m.
Got it. Thank you.
No problem. Anybody else?
I'm looking on Canvas right now, and the midterm, it still says it was due yesterday.
Okay, no problem. I'll fix it. It's not a problem. It might have been just me mixing up when I went to hit the button and I rolled to the left instead of to the right or something stupid like that. But I'll definitely be fixing it right at the end of class. I'll probably be doing it while you're still on here and I'm waiting for questions.
All right, thank you.
It also says chapter 16 to 26. I thought it was only up to 25.
I think that might be a typo because I'm pretty confident. Let me go over there right now to double check, but I'm pretty confident I left out 26. But I will check that right now because obviously that'd be a bit of a problem.
Yeah, I was gonna order pizza for later.
Somebody's gonna order pizza for later. Yay!
Pizza sounds good.
Hold on.
Sorry, am I not on mute?
That's okay.
Oh, did you guys hear how excited I was to take the test from home?
Yes, you can take the test from home, and you just have to use the lockdown browser stuff. Yes, it does say 16 to 26, and it does say October 30th. I'll go ahead and fix both of those now. I'm going to look at that and look at what we've got. Yes, in fact, it did have chapter 26 in it, and that is definitely a problem. So I'm going to count those three. There's 3 problems from chapter 26. I'll count those as extra credit completely. And I'm going to do that with my other class already, because that was not supposed to be there. And I did in fact put them in. So that's my screw up, not yours. Now I'll go back to the settings, and it's going to be due tonight at 11:59 p.m. And then it's going to disappear at that time as well. So hopefully that'll help you. So there are 3 questions. They're actually worth quite a lot, by the way. There are 3 questions from chapter 26, but I do remember specifically it wasn't supposed to have the 26 in there. So I'll just make them as extra credit, and I'll have to regroup and regrade everything when it's done. But if you get a good grade on the test tonight and it reports a good grade when you're done, then you've really done an amazing job, because there's a lot of points in those 3 questions that weren't supposed to count at all. And it looks like I don't have, there's also an access code. That won't be necessary. I'm going to erase that now. Problem is, when I erase it, it doesn't necessarily disappear. So I got to make sure I do it in 2 different places. So I'm going to erase that access code. I had to put it up there just so people wouldn't take it at a random time. So that's why I did it initially. And here it is. So no access code. And you'll have to give me about at least 10 minutes after class to update that. Just because it's got a part in there where I've got to put my own instructions in. So just don't start it till we get out at what, 6:20. I'd say don't start it till 6:40 at least. So hopefully
we get out at 6:40.
Oh, 6:40, thank you. So don't start it till any earlier than 7 o'clock. That'd probably be best. And y'all can, like I said, go ahead and wait till 10 if you want to. Does anybody feel like you might need to start a little later than 10? Because I could push it back and allow you to start like at 11 if you wanted to. I know tonight's Halloween. I'm trying to minimize the impact on your life. As young college people, y'all might either have family or just have some fun plans. So I can do it even, I mean, I don't think you want to go out and party and then take a test, but I could definitely push it further back if you wanted.
So I'm already at campus. Is Miss R still going to be here?
She's not going to be there now.
Oh, okay.
No problem. Anybody else have anything? All right, so just don't start the test before 7. You should be golden. When we last met, assuming we don't have any more questions, so when we last met, I gave you some equations. For instance, I gave you the equation for the strength of the magnetic field caused by current carrying wire. We found that magnetic field had a strength that was mu0 times I, the current that the wire carries, and mu0 is a constant, 4 pi times 10 to the negative 7th Tesla meters per amp. And then it was mu0 I divided by parentheses 2 pi r, where r is the distance, the perpendicular distance from the line that you can sort of treat as the center of the line of the wire carrying the current out to the position at which you wish to know the magnetic field. And that will actually calculate that. Of course, you got to put the distance in meters, and you need to use the right-hand rule to figure out the direction. And the right-hand rule says if you put your thumb in the direction of the current carrying wire, in the direction that the current's going, you wrap your right fingers around it, and then those fingers are coiling around the wire in the direction that the magnetic field points. We also said the force on a current carrying wire submerged in a magnetic field, or submerged is not necessarily the best word, but you get what I'm saying, within a magnetic field. And that was sort of the F equals Bill equation, but I told you it's really from a cross product. So it's I L cross B if you have a nice uniform wire that's not going to change over positions. If you actually have a wire whose orientation with respect to the magnetic field changes, or a magnetic field that changes as a function of position, then you have to use an integral form, which we'll work on tonight. And I also gave you F equals QV cross B, which is the force on a charge Q moving with a velocity V in a magnetic field B. That is a point by point type thing. So you could actually use that at any particular location, and that'll give you the force at that particular location. So you just have to know the charge that the particle has at that location, the velocity that it has. Of course, if the charge is negative, then QV is actually going to be the opposite direction as V. And then the magnetic field you have to have as well. And then you got to do that cross product. And then finally, we said, okay, if you put one wire next to another wire, then one wire can be thought of as the source of the magnetic field. And then the other wire is going to feel that magnetic field and get a force from it using the F equals Bill equation. So I worked out an equation like that. So that was the stuff we actually worked out. Now what we're going to do is I'm going to go ahead and show you an example with those. So let me start by sharing my screen. And that might take a few seconds to start it or to share it. So we'll go ahead and I'm going to start working a problem just as soon as the screen comes up, of course. Still waiting on it. Still waiting. Still waiting. Okay, now we're there. So first off, I want to remind you the equations that we found. So I'm going to write those equations again. The first thing I said was B is equal to mu 0 I over 2 pi R, and mu 0 is equal to 4 pi times 10 to the negative 7th Tesla meters per amp, like that. Also said that F, or let's write it differentially, dF is equal to I dL cross B, and that ultimately reduces to the F equals Bill equation where you have BIL sine theta. And then we also had F is equal to QV cross B, or more specifically, the total force that you could have would be Q times E, where E is the electric field, plus Q times V cross B, and that's called the Lorentz force law. Okay, now you could combine, for instance, that equation for B and that F equals Bill equation to get the force on one wire due to the other wire. And what you discover is that two parallel wires tend to be attracted to one another. So there's a force of attraction between them, assuming the two currents going in the same direction. But if the two parallel wires have currents going in the opposite direction, then they tend to repel each other. And that's a typical calculation that you should be able to do. I think it's fairly trivial. As I mentioned to you, it's often that you calculate the force per unit length as opposed to the force, but either way, that should help you. So now let's look at a problem where I'm going to say we have a wire that's going to run up, and then it's going to go to a half circle. I said it's a half circle, stupid computer, but it's not letting me do that. Let's see if I can do this. No, that still looks like something other than a half circle. So I'm going to erase that part, and I am going to draw my half circle on my own like that. And then the wire goes this way as well. And what I'm going to do is, again, this is supposed to be a half circle. It clearly is a little bit less than a half circle, but the main thing is we're going to pretend like it's a half circle. Now, I'm also going to say that this particular wire is going to be carrying a current, and it's actually immersed in a uniform magnetic field that you can see by these little red X's, which suggests that the magnetic field is pointing into the board. And what we'd like to do is calculate the force acting on it. And what I'm going to do is I'm going to say that the current is going up on this side, then it's going around this way, and then it's going back down this way, and the current is in fact just plain I. the magnetic field is just plain B, which I'm going to say is equal to the constant B times K hat. And now I'm going to create my coordinate system as if it's directly at the quote unquote center of the half circle. So there's my x-axis. And then this is my y-axis, like that. And of course, that means by the right-hand rule, remember your coordinate systems have to be right-handed. So if you take I hat and then cross it with J hat, then you should get K hat. And that means in this case, the Z axis would be pointing out of the board. So I should technically call this negative B K hat. Okay. Any questions on that? All right. So the force we're going to use, well, actually, let me go ahead and label something on here. This radius of the circle, even though again it doesn't really look like a circle, that radius is going to be called R, and we're going to assume we know I, B, and R. Okay, and what we want to calculate is what is the total force on the wire. Okay. So I'm going to say solution. And now I'm going to show you how to use this somewhat complicated looking formula, which is dF is equal to IDL crossed with B. So that's a typical cross product type thing. I'm going to show you a neat new way to do a cross product, and I'm going to show you exactly how this has worked out. So let's imagine for a second that, let me see, I think I want to use a different color here. Let's see what color I would like to use. Yeah, maybe I'll use this. So let's imagine this little line right here is up an angle theta. Notice that's the same theta that you're used to from like polar coordinates, but I'm going to let theta vary by just a little bit so that it goes from theta to theta plus d theta. And then what we see is when I go to use dF equals IDL cross B, I'm supposed to create a tangent vector, which means a vector that's tangent to the wire in this case. And that tangent vector is going to be called DL. It should in some sense be infinitesimally long and tangential to the wire and pointing in the same direction as the current. That's the main thing about IDL is the DL has to point in the same direction as the current. So in this case, like I said, this little angle right here is d theta. And then I'm going to draw the vector DL, and I need to really look at it up close. So I'm going to zoom into that. But right now, what I'll say is the DL vector looks like this. It's just that itty bitty vector right there. Okay. And that's going to be DL. And I think you can tell that DL is in fact going to have a length that's R times d theta, and then it's going to point in a direction that increases with increasing theta. So just for the record, I'm going to call it theta hat. That is actually a real name. That's an actual real vector. It happens to be, in this case, the vector for the cylindrical coordinates, one of the basis vectors, sort of like I hat, J hat, and K hat are for X, Y, and Z. There's one for cylindrical coordinates that's R hat, theta hat, and K hat. And then there's one for spherical coordinates, a set of vectors. In that case, it would often be called R hat, theta hat, and phi hat. So we're actually doing that, but we don't have to know any of that, even though I do give you an intro to it in our Canvas page and on my YouTube channel. I'm going to just work it out as if I called it theta hat and work out what that is. So to do that, what I'm going to do is zoom in on that little area of the arc. So let's imagine for a second that the arc goes like this, and that coming from the side is this line, and then this line, okay? And that little angle, remember, was d theta. So the actual dl vector should be roughly that. And you can see why we would say its length is actually r d theta, from the same old thing that you learned in rotational motion and then you learned in your trig class. Specifically, the arc length s is equal to r times theta, where theta is in radians. Okay, so there's my little dl vector. And if you think about this, you could actually imagine a coordinate system here where we're going to have our x-axis there. We're going to have our y-axis there. You could imagine, for instance, a vector this way, and then, of course, that angle would be theta. And if you made a unit vector that direction, for instance, let's do this weird color just for the heck of it. Maybe if I can ever get the colors to come up. If I made a unit vector there, that unit vector we could call r hat because it points in the direction of increasing r hat. And then we could create another vector, theta hat, because it points in the direction of increasing theta. But notice that the dl vector is actually exactly parallel to it. So that's sort of what we need is we need a unit vector theta hat, which literally its length is just 1, not 1 meter, not 1 anything, just 1 unit. So if I multiply it by r d theta, it will have exactly the right length. Now, what I want to look at on this, and I'll use a slightly different color. I'm going to use a dark gray. What you'll see is that this part right here is the y component of theta hat, and this part right here is the x component of theta hat. And if you look at this angle that I have drawn as theta, that's going to be the same as this angle right here as well. The reason why is the x-axis and the y-axis make 90 degrees. So that means the angle between the y-axis and the r hat vector is 90 minus theta. But r hat and theta hat also make a 90-degree angle. So since the angle between the green vector of r hat and the y-axis is 90 minus theta, then the angle between the y-axis and the green theta hat vector will be 90 minus theta, which is in fact theta. Okay, so that's why we got that. From that, we can say that dl is going to be r d theta, that's its length. And now if I look at this vector as I have it drawn here, notice the x component is actually negative sine theta. Now, technically, it would be negative sine theta times the hypotenuse, but the hypotenuse is 1, so I don't have to actually do that. Actually, let me show it in there anyways. Maybe that'll look a little clearer when you get to your notes. So I'm going to say, using theta hat, since it has a hat, it obviously has a length of 1, and I'll put a square bracket around here. Actually, let's make that all cleaner. So I'm going to put a square bracket here, and I'm going to say there's a negative sign, then there's a 1, and then there's a sine theta that ends up giving me the x component, and then I just have to put an I hat. Dang it, I hate it when it does that. Then I just have to put an I hat after it. and that makes it point to the left because there's a negative there. The I hat points to the right, but the negative makes it point to the left. Now the y component is actually positive, so I'm going to say plus 1 times cosine theta, and then I'll put a j hat on the end, and that actually gives me essentially what I told you was called theta hat. That'll help you in your, if you end up taking statics and dynamics, because a lot of the equations they do use, they sort of magically give it to you. But if you actually understood these theta hat vectors and r hat vectors and all that stuff, you could derive the formulas yourself and make better sense of why they are what they are. In fact, the r hat vector, just for the record, I'll put it over here. This is extra. Oops, I want to do that in a different color. So this is extra. So if you look at the r hat vector that I drew in the little diagram down here in the red, you can probably see that r hat is going to have an x component that is 1 times cosine theta. So I put cosine theta I hat, and then the y component is going to be 1 times sine theta. So it'll be plus sine theta j hat. And guess what? That is exactly the r hat vector as we know it. Now, here's the neat thing. Theta hat, which we just derived, is negative sine theta I hat plus cosine theta j hat. And if you look at those, I think you'll realize that dr hat over d theta is in fact equal to negative sine theta I hat plus cosine theta j hat, because the derivative of cosine is negative sine and the derivative of sine is cosine. So you end up getting just theta hat. So all that's just some extra stuff I gave you. And hopefully you'll remember that when you get to your statics or dynamics classes for you, those of you who are majoring in engineering. So now we've got our DL vector. Notice it does point in the positive theta hat direction, and it gives us exactly the coordinates we want and all that good stuff. It's got the size that we want. So now I can go ahead and complete my calculation of f, because f is going to be equal to the integral of df, which equals I times the integral of dl cross b. So when you look at your book, you'll notice that one way you can do this is you realize that that theta hat direction really is the direction of the DL vector. And then you could actually compute what its x component is, what its y component is. And then looking at it from a symmetry standpoint, you see that the x component, when you actually take the cross product, is going to give you a force that points like to the left on one half and to the right on the other half. So they're going to cancel out. So you really should only get a y component left. That's a really ingenious physics trick to do. But I'm choosing to show you the details because I think you're probably maybe a little bit more math savvy than you are physics savvy at this point, but maybe not. But I'll explain it again when we're done so that you can see how to do it the other way as well. And you can do it either way you want. I'm just giving you a couple ways. So now I can go ahead and write what IDL is. So I'm going to say equals, I've got my I here, and now I'm going to integrate, and I'm going to integrate from theta. By the way, I'm doing the arc part first. I will work out the straight line part in a second, but that one doesn't require any math because you can see from symmetry it's going to disappear. But I'm going to go from theta equals 0 to theta equals pi, which is basically 180 degrees. The DL, as I said, is going to be R d theta times negative sine theta I hat plus cosine theta j hat, and then this beast is going to be crossed with negative b k hat. So this is where I'm going to show you another way of doing the cross product. I'm going to start off by taking the r and the negative b and the signs and all that stuff. I want to take them out, but right now, the one thing I can definitely take out is the negative b, the r, and the I is already out. So I'll say negative b I r times the integral from 0 to pi of, now I'm going to take, since I've gotten rid of that b, which is basically just using the fact that the cross product is a linear operator, like I've been telling you about the dot product. So now I'm going to have negative sine theta I hat plus cosine theta j hat crossed with k hat, and then of course there's going to be a d theta after it. So now all I have to do is term by term do the cross product. I'll get negative b I r integral 0 to pi, and now I'm going to take and do negative sine theta. And now notice the negative sine theta I pulled out in front, and now all I have to do is I hat cross k hat. I hat cross k hat. And then I also have the cosine theta j hat term is going to hit the cross product as well. So I'm going to get plus cosine theta j hat cross k hat, and then of course all that's times d theta, so we can do our integral. Now I'm going to put the equals way over here so I can have more room. Again, I'm going to write b times I times r with the negative sign out in front. And what I want you to realize is that we have a formula for a cross product. Specifically, the magnitude of a cross product is a cross b magnitude is equal to the magnitude of a times the magnitude of b times the sine of the angle between them when they're tail to tail. So this would be a, and this would be b, and this would be the angle theta. So if I look at I hat cross j hat using that definition, we see that this should be 1 because the magnitude of I is 1 times 1 because the magnitude of k is 1 times the sine of 90 degrees, which is 1. Okay. Then all we have to do is use our right-hand rule to compute what I hat cross k hat is. So using your right-hand rule like this, the I hat is the first vector, so that points along the positive x-axis, which is to our right. And then the k hat points out of the page, which makes us do like that. And you see that the force in this case is going to be in the negative j hat direction. So, or the cross product is going to be in the negative j hat direction. So that's what our cross product is there. Now I can do the same thing here. Let me put this j hat cross k hat in parentheses. And in this case, the same thing happens. You get 1 times 1 times 1 again. But now you use the right-hand rule, which says j hat with this finger, k hat with this finger, and then this is the answer. So if I stick my finger, my index finger, in the upward direction, which is the positive y direction, and then I take the k hat and point my middle finger in that direction, that's into the board. So I have it right there. What I'll see here is the force is actually to the left, which is negative I hat. So I will put negative I hat here, and that's what that cross product is. So now I can continue writing, and actually that negative looks like a oopsie, so I'm going to clean that up a little bit. I'm going to say equals negative b I r integral 0 to pi. Now notice the negative sign times a negative j hat is just going to give a positive sine theta j hat, and then the cosine theta times negative I hat will give a minus cosine theta I hat. And then all of this is times d theta. Okay. So you probably know that the derivative of cosine is negative sine. So the integral of sine should be negative cosine. So I'm going to go ahead and write that way and say this is equal to negative BIR times, in this case, I have negative cosine theta from 0 to pi, and I'll put brackets around it like that, and I'm going to say that's j hat times that, and then I'm going to say minus. Now the derivative of sine is cosine, so the integral of cosine is sine, so I'm just going to write sine theta here, and again that's going to be evaluated from 0 to pi, and then the result is going to be multiplied by the I hat. Okay, now I've completed the integration process, and I get negative b times I times r times, now I take the cosine, negative of cosine of pi. The cosine of pi is -1, so the negative of that will be +1. And then it's minus the cosine of 0, and minus the cosine of 0 is 1, so minus that would be -1, and then multiply that by 1, I mean by -1, you get +1 again, so that'd be 2 ultimately, and all that times j hat. And when you do sine, you end up getting sine of pi is 0 minus the sine of 0 is also 0, and you get that times I hat. And as I had hinted to earlier, yeah, we should expect the y component, or excuse me, the x component to cancel out from the symmetry of the problem. So ultimately, all we have is that the force due to the semicircular loop, so I'll say SC, is just equal to negative 2BIR j hat. And that's actually going to be the whole answer. So I'll go ahead and circle it, but now I'm going to explain to you why. If you look at the straight wire on the right-hand side going from below the x-axis up to the x-axis, can anybody tell me which direction the force due to that magnetic field would act on that straight wire? You got to use your right-hand rule here. I've opened up the chat too in case somebody's answering it that way. So remember, we're using the F equals Bill, and that means IL cross B. So you want to point your finger in the direction of I and therefore L as well. That's that finger. And then you want your middle finger to point in the direction of B, and then your thumb is going to tell you which direction the force is acting. So which direction is the force acting on the right-hand vertical wire? No guesses? All right, so the current is going up, so I put my finger that way. That means my middle finger can point any direction. I just got to make sure that index finger stays pointing up. But what I find is the magnetic field goes into the board, so I have to orient my hand this way. Now the magnetic field, my middle finger can point in the direction of the magnetic field, which is into the screen, and the force is to the left. So what I'm going to do right here is say that is FL. And remember, the magnitude of FL would be the magnitude of magnetic field B times the current I times the length that is, which basically goes from here to here. But that's also the same as the length from here to here on this wire. So now I'm going to compute the direction of the force on the wire on the, why did I say R, L? Sorry about that, everybody. I evidently forgot my left and my right and called that F left, but it should be F right. I think what happened is I actually was thinking that it was pointing to the left and I called it left based on that instead of right based on the wire that's to the right. So this is F right, which means due to the right wire. Okay. So can somebody tell me, ooh, that's really small. Can anybody tell me what direction the force on the left wire will point? Anyone? Okay. So again, I'll take my index finger and I'm going to point in the direction of the current, which is down. Now I've got to turn my hand so that my middle finger can point in the direction of the magnetic field, which forces me to do in this direction, but my computer keeps wanting to aim it on my head instead of my finger. But basically what you see is my thumb now points to the right. So this force over here is going to be FL, and it points that way. And notice they'll be exactly equal. So the magnitude of FL is equal to the magnitude of FR. So magnitude FL equals magnitude FR. Therefore, FL plus FR equals 0. So F total is equal to -2 BIR J hat, and that's the final answer. Any questions on that? Okay, so that's the typical type of integral calculation that you do for this type of course. You'll see a much uglier one when we get to the next chapter, because we're going to introduce the law of Biot-Savart, B-I-O-T hyphen S-A-V-A-R-T. That's got a cross product in the integral just like this one does, only it's even uglier. So this is a good starter problem, if you will, for preparing you to start doing these problems. If you wanted to actually do this sort of like the book does, it's the same ultimate result, but you've got to be a little bit more physically ingenious. So let me show you real quickly how you could go about doing that. I'm going to again try to draw a half circle in some meaningful way. So I'm going to say that the radius is going to be 3 squares. That means it should be 3 squares over there and 3 squares over there and about 3 squares there. So I'm going to attempt to draw it like this. That looks pretty good, not too bad anyways. This is going to be straight, and this is going to be straight here as well. Again, I'm going to call this radius right here R. Okay. I'm going to treat this little segment right here where I did a bad job on drawing my circle. I'm going to treat that as my little differential area element. And I'm going to zoom in on it so I can erase it a little bit. Okay. So what I'm going to do is now I'm going to draw a line from here to there, and then from there to there. And I'm going to realize that this vector is my DL vector. Okay. And then I'm also going to realize that my magnetic field vectors are essentially pointing into the page like this and uniform. Okay. So when I do I dl cross b, because remember the current I is going up there, and then it's going that way and that way and that way. So when I do I dl cross b, dl has to go this way, diagonally up and to the left. The magnetic field is into the board, so I have to turn my hand this way. And what I see is, in this case, the actual vector force points radially inward. So at that point, I can say this is df, which equals I dl cross b. Now, with that in mind, you realize that is radially inward. So you could sort of imagine, for instance, that this is radially outward, and that would be the angle theta that we're up here, which is also theta here. So you could say that the df vector is actually parallel. Let's not write it that way. Let's write it parallel to negative r hat. Remember, r hat points radially outward. So if I put a negative in front of it, it's going to point radially inward. And if I wanted to work out r hat or work out negative r hat, then that means df. Now I can shrink it back up. That means that df is going to be equal to, we can see that cosine of theta times 1 would give me the x component, but I need the negative of that. So I'm going to say negative cosine theta I hat. And then the y component would be sine theta, but again, that's positive. So I'll need minus sine theta times 1 j hat, like that. So that's what our df vector is. And all we really need to understand then is the magnitude of it is going to be b times dl times b times dl times I. So because it's f equals df is equal to I dl cross b, that says the magnitude of df is just I dl v sine theta. Okay, but notice that the dl and the b are perfectly perpendicular. So this quantity right here is 90 degrees, which means this quantity right here is just 1. So I only need that. Now, here's where you make your argument. Notice that it's always going to be radially inward. So for instance, when I go over to here, I'm going to have a dl that points this way. But if you work out I dl cross b on this one, you get that the force df is radially inward again. So what you see is on this left-hand side, you've got a negative x component and a negative y component. And then on the right-hand side, you've got a positive x component and a negative y component. So the x components are going to cancel each other out by symmetry, because there's just as much x to the right as there is x to the left, only they're opposite in sign. So that tells you that this part right here is going to integrate to 0. So we can say f is equal to I times b times dl, which is r d theta. That's what dl is, times negative sine theta j hat. And that's going to be my df. And notice I don't have a vector part anymore. I shouldn't even write that vector symbol up there. So I erase it like that. So now we can just integrate that, and we get f is equal to the integral of df, which for this case, we're going to do just magnitude. So f is equal to the integral from theta equals 0 to pi of I times, let's do it the other way, B times I times R times negative sine theta d theta j hat. So this gives us negative BIR times the integral of sine theta d theta in the j hat direction from 0 to pi. And of course, the cosine, the derivative of negative cosine is positive sine. So the integral should be negative cosine. So I get negative BIR j hat times negative cosine theta from 0 to pi, which I can take that negative and combine it with the other negative and get positive BIR times j hat. Now cosine of pi is going to be -1 and then minus the cosine of 0, which is 1. So I end up getting -2 BIR j hat, which took a lot less lines, right? But I think the reasoning through it was a little more complicated. So hopefully that'll help you in trying to make sense of the books example. So definitely look this over, look at the books example, look at this other example as well. Y'all should be able to actually pull off this kind of problem and specifically practice that particular problem. That would be really a good thing to do. So just practice that problem, close your book, see if you can write it out from the very beginning, and then try to come up with each individual part, work out all the integrals, get the answer, and see if you get 2 BIR j hat. And notice in this case, since the magnetic field is pointing into the board, the force on that semicircular part is pointing downward in the negative y direction. Any questions on that? All right, so there's two other concepts I want to get to you before I let you guys go. One of them is a velocity selector. So let's look at velocity selector. So in currently, I don't know of any everyday Joe uses of a velocity selector, but I can imagine that sometime in the future there might be a need for such technology for everyday people. In other words, there might be some kind of widget, if you will, that can make use of the fact that you can choose a specific velocity and only that specific velocity to do some kind of thing, right? Right now, what we have is when we do experiments where we're trying to, let's say, bombard a nucleus with a charged particle, then we really want to know how much energy the charged particle came in with. And one way we could do that is by giving the charged particle a very specific velocity. That's easier said than done, but you can take a bunch of velocities, say a bunch of charged particles coming through at various velocities, and then make a device that only allows a certain velocity through, and that's what the velocity selector is. So with that in mind, let me show you how a velocity selector would work. We're going to imagine, for starters, that we're going to have a little charged particle creator thing to the left of this panel with a hole in it. And then there's going to be a ginormous, there's going to be a ginormous positively charged plate on the top side like this. Sorry about that. So that's the positively charged plate. So we're literally going to imagine it as if it's got a bunch of little positive charges on it, like that. And then down here at the bottom, there is going to be, in fact, a negatively charged plate. That sort of looks just like it. But in this case, it'd have a negative charge here, here, and here. the reason this is the case is that basically we're going to get a uniform electric field that points straight down. Remember, the electric field points in the direction that a positive charge is compelled to go by it. So that's the electric field E there. Now, if we actually put a charged particle in here, let's say this little guy right here happened to come from that little hole, and I'll just assume it's a positive charge for right now, but what you'll find out is what I work out here will give us the same answer, whether it's a positively charged particle or a negatively charged particle, but it's going to come in with a velocity v. Okay. Now, can anybody tell me which direction this positive charge is going to be deflected as a result of this this electric field?
Down.
Yes, it's going to be deflected downward. As we all know, of course, that's the direction that the electric field is supposed to point, is the direction that a positive charge would go. So yeah, we're going to do that. But what if I were to tell you we can create a magnetic field in that same area, and that magnetic field could be used to counteract the effect of the electric field? So we want a magnetic field that actually would tend to cause the positive particle to move up. Which direction should our magnetic field point? I'll give you some choices like left, right, into the page, out of the page, up or down. You're going to use your right hand rule, and you're going to remember that the force due to magnetism on a charged particle Q with a velocity v is QV cross B. So your QV vector should point in the direction of your index finger, with your B, with your middle finger pointing in the direction of B and your right thumb pointing in the direction of force. We want the force to be upward. So which direction should the magnetic field point? So you can start, notice your right hand's like this, right? And we want the force to point up. So I'll just turn my hand like that. Now I'm going to adjust my finger to point in the direction of the QV. Well, the charged particle is positive, so QV is the same direction as V, and my finger happens to be pointing that direction already. So I can tell that I want the magnetic field pointing into the page. So that's what we're going to do. We're going to say there's a magnetic field, and we're going to set it up pointing into the page. So right here, whoa, Nelly. Right here is a magnetic field pointing into the page, into the page. I'm doing about 4 there. So into the page, 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 like that. And it's going to be basically uniform. So what we would do is try to actually put this plate in between a north and south pole of 2 different magnets. We'd have the north pole out here in front of the screen and the south pole back behind it. And that would make a uniform magnetic field going into the page. And then over here, what we do is put yet another plate. And this plate would have a very small hole in it as well. And what we'd want it to do is be perfectly lined up so that only particles that go through there directly and straight will actually make it through. Now, there will be some room for error, obviously, if the velocity is off by, a 1 in the 12 millionth decimal place, it's probably still going to go through. But those are all things you can control, and you can make sure the hole and the magnetic field and the electric field all have uncertainties that are small enough to account for that. But when you do that now, you're going to have basically a force up is going to be Q times V times B. Notice the Q times V times B. The V is perpendicular to the B, so I don't have to have the sine theta. I don't have to have the cross product. I can just do that. And then I'm going to set that equal to the force that's down. And of course, that force is Q times E. So we get QVB is equal to QE. The charge actually cancels out. And that's the part where I was telling you it wouldn't matter whether the charge is positive or negative. It's going to work out either way. And from this, we get that the velocity is going to be the ratio of the electric field and the magnetic field. So that's the actual velocity for the velocity selector. So if your velocity is a little higher than E over B, then that's going to make the magnetic field force a little bit stronger, and that's going to cause it to deviate up and miss the hole. If the velocity is a little bit lower than E over B, then that's going to make the electric field strength a little stronger, or actually it makes it about the same, but it's going to make the magnetic field weaker. So it's going to tend to go down below the hole, and they're going to hit the plate. So you can do that, and then using those ideas of uncertainty in the electric field, uncertainty in the magnetic field, and diameter of the hole, you can nail that down to where you only get velocities between, let's say, 2 times 10 to the 7th plus or minus 0.001 times 10 to the 7th meters per second. So you could literally get it down to 3 decimal places, 4 decimal places, whatever. And that's how a velocity selector would work. Any questions on that? All right, we only got about 19 minutes left. I want to do one more thing. So this is like electric motor that we've discussed before and you saw in your Faraday lab. But let's imagine that we are making an axle. So this is an axle. Okay. Now that axle will be allowed to rotate either by putting it in bearings so that it can freely rotate, or we could actually like connect it to a drill and make it rotate ourselves. So either way we want to do it's fine. But what I'm now going to do is I'm going to take a bit of wire and I'm going to run it and attach it to the sides of this axle. And then it's going to go out here. But now I'm going to make sure it's nice and thick wire, so that I can form it and it make a shape, a very specific shape. And this specific shape is going to be a rectangular shape like this. So now I'm going to go over 3 plus 2 plus 3 more. So 1, 2, 3 plus 2 plus 1, 2, 3 like that. And then this is going to come back down here. And now it's going to come back there. And then this one's going to run down the side and then be released. Now, if this axle's spinning, obviously these wires are going to wrap all around. So in practice, what you're going to have to do is put like a split ring or something like that to make the conductive contact without the wire actually wrapping around. But that's a idiosyncrasy we don't have to worry too much about. But what we're going to imagine is a current I going in here and then hanging a left and then going up and then going to the right and then going down and then hanging a left again and now leaving it. Okay, so that's our current I. And what we're going to also imagine is there is a fairly uniform magnetic field B that's pointing from right to left like this. Actually, I don't want that one. Like that. Okay. Now, what we're trying to do is calculate the torque on this. If you look at the net force, you can see that the top wire, notice in the top, IDL is parallel to B. That implies F equals 0. Okay. Same thing with the bottom. F equals 0. F equals 0, right? Now, you might also realize that the force on the left side and the force on the right side are in opposite directions, and therefore they would add up to give you 0. And you'd be right. The net force on this will be 0, but the net torque on this will not be 0. So can anybody tell me in which direction the force will act on the left-hand side? In other words, between here and here, which direction will the force act as a result of that current and that magnetic field? You can think of it as the current is actually positive particles. That's the conventional current crap that we use. So you could say QV is the same direction as I. So QV cross B, and that would give you your force. Anybody have a direction for that force yet?
Outside of the paper, like towards house.
Yes, you could be in the paper or out of the paper. Do you think it's outside of the paper here, or do you think it's pointing into the paper here?
Out of the paper.
Out of the paper. So when I do it, I say IDL. Okay, so that points up for that left-hand wire, and then the magnetic field points to the right. So I have to turn my hand like this, and now I see my thumbs pointing into the page. So in this case, it's actually in the page. So the force is that. Okay. Now on the other side, you get a force as well, but IDL points down, the magnetic field points to the right, so F points out. So in this case, the force is out. Okay, but thank you for trying. I don't know, you might not have saw which direction my magnetic fields were pointing or something like that, but the main thing is the positive charge is going up makes a current, and that current means QV or IDL goes up, and then B going to the right forces it to be in. So what we get is actually a torque. Now, if I say this dimension right here, actually let's use a different color. I'm going to use this color. Let's call this dimension right here A. And let's call this dimension from here to here, let's call that B. And then let's look from above. So view from above. So in other words, I'm looking at the diagram I have right now, but I'm looking from up above the screen looking downward. So when I do that, what I'm going to have is a current carrying wire that goes from here to here. And the current is actually going this way. And what I see is a force that was supposed to be black. So what I see is a force going that way and another force going that way. Okay. So do y'all agree that this is a clockwise torque? So the torque is clockwise. Let's calculate the torque. So remember also that this dimension from here to here is A. So the torque due to the left is equal to, remember it's force times lever arm. So the lever arm is A over 2. The force is F equals Bill. So that would be the strength of the magnetic field, the current times the length. And in this case, the length is B. And then the torque due to the right one, which is also clockwise, is going to be A over 2 B times I times lowercase b. So T total is equal to torque left plus torque right because both are clockwise. Okay. So with this, I get that the torque total is equal to, I got A over 2 BIB plus A over 2 BIB. So I'm going to write this as B times I times AB. Because the A over 2 plus A over 2 just gives us A. Can anybody tell me from a geometric standpoint, what is A times B? This A times B.
Area?
Yes, this is the area. And in fact, remember we learned about the electric dipole, P was equal to QD. Well, there's a magnetic dipole that's called mu. So we often will define mu equals the magnetic dipole moment. And that's going to be defined as, in case you have more than one wire, it'll be N, where N is the number of turns, times I times the area. Okay, that's going to be the magnetic dipole moment, and it'll be a vector because it'll have a coordinate, a direction that's perpendicular to the plane of the area. And when I say perpendicular to the plane of the area, since the plane, as you can see right here, is the plane of the page, there is a perpendicular vector pointing at us, and there's another one pointing away from us. Well, the way you decide on which one to use is you use your right hand and let your fingers curl around the loop in the same direction as the current is going, which in this case, we see the current in the top picture is going clockwise. So that means I have to put my hand like this with my thumb pointing into the board. So in this case, the vector would actually point into the page. So N above, N points into page. So then what we can see is a really nice simplification, which is that torque is actually equal to mu cross B. And that's really what we were shooting for here, is torque is equal to mu cross B. Anybody have any questions on that? I was actually looking for where I did that part. Let's see. There it is. Torque on current loop. Yeah, so torque is equal to mu cross B. And you can follow the argument in your book, but basically, I should also say where mu is equal to N times I times A vector. So sometimes we generally we never actually write that little N hat. What we really do is we make a vector whose length is equal to the area of the actual loop, and then use the right hand rule to define its direction. And that's what that is. We also know that U, the potential energy for this, and you can work it out yourself, is negative mu dot B. So compare that, for instance, to torque is equal to P cross E for the electric dipole, and U is equal to negative P dot E for the electric dipole. So you see that they're exactly on the same footing, and that's the main thing I wanted to do here, is show you that. Anybody have any questions on that? All right, we're actually done, guys. You are free to go. Remember, you're supposed to start your test unless someone asks me for a later time in the next couple minutes. You're supposed to start at no later than 10, and you're allowed 2 full hours. I've got to go in and change something really quick, so don't start it until 7 at least. But you guys are free to go. I hope you all do really, really, really well. Remember, the last 3 questions on there are going to be from chapter 26. That was a boo-boo on my behalf. So they're just going to count as extra credit, meaning the worst thing that could happen is you got all 3 of them wrong and you get 0 points taken off. The best thing you can happen to you is that you get them right and you can get a lot of points added to your test. Okay, so don't feel bad if you don't get those last 3. That was not supposed to be on there at all. So good luck and kick some butt, and I hope you all have a good evening, and I will see you on Thursday.
Professor, I did have a question.
Yes.
So you said that like our formula sheet's allowed to be like as long as we want. And you basically said that we should have essentially all of the formulas from all of the chapters. So my formula sheet is like 13 pages long. And
Right.
during the part where it has us like show the room and stuff, I don't
Right.
think I have enough time to show all of my formula sheets.
That's okay.
So
Yeah,
okay.
yeah, don't worry about it. I'll ask you to do it, but if you really have 13 pages, yeah, there's not it. Try just taking the pages that have the most recent stuff. Maybe you've got 2 or 3 of those. Just show those. That'll be sufficient.
Okay.
Okay.
Yeah, the way that I have it set up right now, I have like a chapter per page for the last few chapters. That's probably like inflating the number a lot. Like the entire first like Physics 241
Uh-huh.
fits on like 3 pages. But then the rest of it is yeah.
Gotcha. Okay. So
Anyways.
yeah, if it takes too long, don't worry too much about it. But the time doesn't start counting until you start doing the test. So that's not going to come from your 2 hours. But yeah, I wouldn't want to waste a lot.
No. I knew that, but like when it has you record the video,
Right.
it only gives like it stops the video automatically after a certain point.
Oh, I didn't know that. Okay, gotcha.
Yeah.
Well,
So
that's cool.
I've
Sorry about
had
it.
the issue where I wasn't able to show the whole room before
Right.
because like because I was showing formula sheets for most of the time and I didn't realize it was going to cut me off, so I had to like retake that video and
Gotcha.
yeah.
Well, yeah, we'll be somewhat on the honor system anyway. So just, do your best and don't worry too much. To say, I talked to you about it. Here it is, and I'll see that on the video. It'll be fine.
Okay.
All right. Good luck,
All right.
man.
Thank you. Have a good one.
You too. Anybody else? All right, I'm finishing the stuff that I said I needed to get done. It looks like I'm going to have it done before.
Hey, Professor, I've got a question for you.
Yes.
It's not related to the test we're about to take, but it's about the online test from last week that I talked to you about. I didn't see it get opened back up last week. Is there any way I could you could open it up for this week?
Yeah. What's your name?
Various.
Was that?
Various Walker.
Various Walker. Gotcha. And that was like test 6 or something, or test.
Yeah, it was. I'll have to look it up, but it was like the last test we were supposed to take online.
Okay, no problem. I'll double check with that. Make sure I'm ready to roll it, and I'll give you like a week.
And I'll shoot you a text too, because I think you asked me to shoot you a text. I've been so busy that I was just looking every day for it to come up, but I'll shoot you a text just to remind you.
That would help. Thank you.
Okay, thanks, Mr. Aaron.
Have a good one.
Professor Young,
Yes.
quick question. So for this test, it's going to replace whichever one is the lowest of the 2, correct? Or
Except the final can't be done. We're never going to drop the final. The final's not optional and that kind of thing. But yeah, between the last one and this one, you only get the higher of the 2.
Okay, cool. Thank you.
No problem.
Have a good weekend, or not weekend, because I'll see you Thursday.
No, I'm going to have one anyway.
So does that mean if I score worse on this test than I did on the first test, that like I still get the grade from my first test?
Yes.
Oh, okay.
Make you feel a little better?
I mean, yeah, I did good on the first test, so
Yeah, and I have a sneaky suspicion you'll do well on this one. How about that?
Well, thank you.
All right. Have a good one, Taylor.
You too.
Anybody else? Haley? Randall? All right, I'm going to check that test for my student. And I think I will check and see what test he missed. That will help. Various. Taylor, you still there? Haley, you still there? We'll stop sharing now.
Have a great night, Professor.
You too, Haley. Have a good test. I hope you do well. Happy Halloween.
Thank you. Happy Halloween.
Bye-bye.
Bye.